Hi everybody, welcome back to the Feynman technique. Today we're going to be deriving this a formula for this generalized half factorial, meaning things like 1/2 factorial, 3 halves, 5 halves, etc. And we're going to be using these two facts that I've previously shown on the channel. This is the half Gaussian integral, which is equal to the square root of pi over 2. And this is a generalized factorial. This is the integral representation of the factorial function. And also, we'll just be using this fact about factorials. This is just the way the factorial function behaves. N plus 1 factorial is always going to be equal to n plus 1 times n factorial. Okay. So where we're going to start is here. We're going to find negative 1/2 factorial, which I've already shown on this channel, but I'll do it one more time. So from this formula, we know that negative 1/2 factorial is equal to the integral from 0 to infinity of x to the negative 1/2 times e to the negative x dx, making the substitution that x is equal to u squared. We get that x to the negative 1/2 is equal to u to the negative 1, and that dx is equal to 2u du. All right, let's do that substitution. All right, so the bounds of integration don't change, and we'd have, let's see, this x to the negative 1/2 would become u to the negative 1, which would cancel with this u from our dx. We'd be left with a 2 e to the negative u squared du, which is equal to the square root of pi from this formula right here. All right, so we get to start now with that negative 1/2 factorial is equal to the square root of pi. And negative 1/2 factorial is the easiest non-integer or non-natural number factorial to derive because of this. Because of this and this. So that's why I started with a negative 1/2 factorial. And from there, we can use this fact about factorials to kind of get to build a pattern. And I'll show you really quick. Let's set n plus 1 equal to 1/2. All right. So that would mean that 1/2 factorial is equal to, well, we said n plus 1 was 1/2, so that's going to be 1/2 times, well, what's n? If n plus 1 is 1/2, then n is negative 1/2. So that's times negative 1/2 factorial. And that would be equal to the square root of pi over 2, since we already know what negative 1/2 factorial is. Square root of pi times 1/2 is square root of pi over 2. All right, so now let's set our n equal to 3 halves. So 3 halves factorial would be equal to, well, we set our n plus 1 equal to 3 halves. Our n plus 1 is 3 halves, so that would be 3 halves times n, or times 1/2 factorial, which we know is the square root of pi over 2. Well, I'll actually write 1/2 factorial. And that's going to be equal to, well, 1/2 factorial is the square root of pi over 2 times 3 halves is 3 square root of pi over 4. All right, we'll do 2 more. 5 halves factorial is equal to 5 halves times 3 halves factorial, which we know from our previous line is 3 square root of pi over 4. So that's going to give us 15 square root of pi over 8. And one more time, 7 halves factorial is equal to 7 halves times 5 halves factorial. And that is going to be equal to, let's see, 7 times 15 is 105 square root of pi over 16. And that's good enough to get the pattern that 2n plus 1 over 2 factorial is going to be equal to 2n plus 1 double factorial over 2 to the n plus 1 times the square root of pi. And let's just check that really quick. All right, let's make our n equal to 3. That would correspond with the last line right here. So if n is 3, then we have 6 plus 1, which is 7 halves factorial, should be equal to 7 double factorial, which is 7 times 5, which is 35, times 3, which is 105, times 1, which is 105, over 2 to the 4th, so 2, 4, 8, 16, which is what we have, times the square root of pi. Yeah, that's right. So that is a generalized formula for the half factorial. I actually should say where n exists in the natural numbers and then union -1. So it's the natural numbers and also -1. The pattern falls apart if you try to let n equal -2. But I might do a video in the future on kind of the negative half factorials. But anyway, there you go. Hope you enjoyed that.